Hi, this is David Quatello with Siemens. In this quick step video, we will be discussing the basics of electricity. And here is just a slide on the legal trademarks. Let's go over some of today's objectives. Upon completion of the course, you'll be able to explain the difference between conductors and insulators, use Ohm's law to calculate current, voltage, and resistance, calculate equivalent resistance for series, parallel, or series parallel circuits, calculate voltage drop across a resistor, calculate power given other basic values, identify factors that determine the strength and polarity of a current carrying coil's magnetic field, determine peak, instantaneous, and effective values of an AC sine wave. Identify factors that affect inductive reactance and capacitive reactance in an AC circuit. Calculate total impedance of a simple AC circuit. Explain the real difference between real power and apparent power in an AC circuit. And determine how a transformer turns ratio affects secondary voltage and current. This course has 4 parts plus a final exam. The first part is an introduction that covers basic electrical concepts. The second part covers direct current, DC, and magnetism. And the final 2 parts cover alternating current, AC circuits. In between each section, we'll also have a knowledge check. All matter is composed atoms. Atoms have a nucleus with electrons orbiting around it. The nucleus is composed of protons and neutrons, which are not shown. In their neutral state, atoms have an equal number of electrons and protons. Electrons have a negative charge, protons have a positive charge, and neutrons are neutral. The negative charge of the electrons is balanced by the positive charge of the protons. Electrons are bound in their orbit by the attraction of the protons. Electrons in the outer band can become free of their orbit by the application of some external force, such as movement through a magnetic field, friction, or chemical action. These are referred to as free electrons. A free electron leaves a void which can be filled by an electron forced out of orbit from another atom. As free electrons move from one atom to the next, an electron flow is produced. This is the basis of electricity. An electric current is produced when free electrons move from one atom to the next. Materials that permit many electrons to move freely are called conductors. Copper, gold, silver, and aluminum are examples of materials that are good conductors. Copper is widely used as a conductor because it's one of the best conductors and is relatively inexpensive. Materials that allow few free electrons are called insulators. Materials such as plastic, rubber, glass, mica, and ceramic are good insulators. An electrical cable is one example of how conductors and insulators are used together. Electrons flow along a copper conductor to provide energy to an electric device, such as a radio, lamp, or motor. An insulator around the outside of the copper conductor is provided to keep electrons in the conductor. Semiconductor materials, such as silicon, can be used to manufacture devices that have characteristics of both the conductors and insulators. Many semiconductor devices act like a conductor when an external force is applied in one direction, and like an insulator when an external force is applied in the opposite direction. This principle is basic to the operation of transistors, diodes, and other solid-state electronic devices. Elements are defined by the number of electrons in orbit around the nucleus of an atom and by the number of protons in the nucleus. A hydrogen atom, for example, has only 1 electron and 1 proton. An aluminum atom has 13 electrons and 13 protons. An atom with an equal number of electrons and protons is said to be electrically neutral. Electrons in the outer band of some atoms are easily displaced by the application of external force. Electrons which are forced out of their orbits can result in a lack of electrons where they leave and an excess of electrons where they come to rest. A material with more protons and electrons has a net positive charge, and a material with more electrons and protons has a net negative charge. A positive or negative charge is caused by an absence or excess of electrons, because the number of protons in an atom normally remains constant. The old saying, opposites attract, is true when dealing with electric charges. Charged bodies have an invisible electric field around them. When two like-charged bodies are brought together, their electric fields repel one body from the other. When two unlike charged bodies are brought together, their electric fields attract one body to the other. The electric field around a charged body forms invisible lines of force. These invisible lines of force cause the attraction or repulsion. The strength of the force of attraction or repulsion is dependent upon both the amount of charge and the distance between the charges. More specifically, the strength of the repulsion or attraction can be increased by increasing the amount of charge and or by reducing the distance between the charges. Electricity is the flow of electrons in a conductor from one atom to the next atom in the same general direction. This flow of electrons is referred to as current. Current that constantly flows in the same direction is called direct current, DC. Current that periodically changes direction is called alternating current, AC. Current in a DC circuit is designated by the symbol I. Current is measured in amperes, which is often shortened to amps. The letter A is the symbol for amps. It's common to use metric unit prefixes when referring to large or small amounts of an item. So, as shown in the accompanying graphic, 1 kiloampere is equal to 1,000 amperes. 1 milliampere is 1,000th of, and 1 microampere is 1 millionth of an ampere. You'll see these and other metric unit prefixes commonly used when referring to units of measure. As the accompanying graphic also shows, kilo is often represented by the letter K, the small letter K. Milli is often represented by the small letter M, and micro is often represented by the Greek letter mu, which looks similar to the letter U. There are two approaches that can be used when analyzing current in electrical circuits. In this course, we'll use electron flow when talking about current because many people find it easier to understand. Therefore, we'll refer to current as the flow of electrons from a negative charge to a positive charge. Be aware, however, that in engineering courses, conventional current flow theory is used. Conventional current flow theory ignores the flow of electrons and states that current flows from positive to negative. The force required to make electrons flow through a conductor is called a voltage, which is also referred to as electromotive force, or EMF, or difference in potential. Voltage in a DC circuit is designated by the capital letter E or the capital letter V. The unit of measurement for voltage is volts, which is also designated by the letter V. As the accompanying graphic shows, metric unit prefixes are used when specifying large or small quantities of voltage. A voltage can be generated in various ways. A battery uses an electrochemical process. A car's alternator and a power plant generator utilizes a magnetic induction process. All voltage sources share the characteristic of an excess of electrons at one terminal and a shortage at the other terminal. This results in difference of potential between the two terminals. For a DC voltage source, the polarity of the terminals does not change, so the resulting current constantly flows in the same direction. However, the terminals of an AC voltage source periodically changes polarity, causing the current flow direction to change with each switch in polarity. A third factor that plays a role in an electrical circuit is resistance. Resistance is the property of a circuit component or material that opposes current flow. All material resists the flow of electrical current to some extent. The amount of resistance depends upon composition, length, cross-section, and temperature of all materials. For any specific material at a constant temperature, the resistance of the material increases with an increase in length or a decrease in cross-section. Resistance is designated by the symbol R. The unit of measurement for resistance is ohms, symbolized by the Greek letter omega, which is the horseshoe shape in the accompanying graphic. Because 1 ohm is a small unit of resistance, kilo and mega are the metric unit prefixes most commonly used when quantifying ohms. While all circuit components have resistance, A resistor is a component manufactured to provide a specific resistance. Most resistors have color-coded bands that identify the amount of resistance. The accompanying diagram also shows the resistor symbol most often used in an electrical diagram. A simple DC circuit can be formed with a voltage source, a resistor, and a conductor to allow electrons to flow from one side of the voltage source through the resistor to the other side of the voltage source. Ohm's law defines the amount of current that will flow in the circuit for a given amount of voltage and resistance. As the formula in the accompanying graphic shows, I is equal to E divided by R, which means that the greater the voltage for a given resistance, the greater the current, and the greater the resistance for a given voltage, the smaller the current. I equals E divided by R is a common way to express Ohm's law. This formula can be easily transposed into two other formulas that also express Ohm's law. E is equal to I times R, and R is equal to E divided by I. The second formula states that voltage is equal to the current multiplied by resistance. The third formula states that resistance is equal to voltage divided by current. All three formulas are needed to understand electrical circuits. Three versions of Ohm's law are needed to understand circuit behavior because we may need to determine any of the three terms when the two other terms are known. As shown in the accompanying example, if we know that the voltage is 10 volts and the resistance is 5 ohms, we can determine that the current is 2 amps. Likewise, if we know that the voltage is 10 volts and the current is 2 amps, we can determine that the resistance is 5 ohms. Finally, if we know the current is 2 amps and the resistance is 5 ohms, we can determine that the voltage must be 10 volts. You may not normally need to analyze circuits as part of your job, but understanding electrical terms and relationships are needed to understand electrical products. Therefore, this course will present some of the most common electrical concepts and relationships. Don't be concerned if you find some of the mathematical concepts challenging. Simply take what you can from the concepts presented and apply them whenever it's appropriate for you. That concludes section 1, so let's do a quick knowledge check. Question 1. Blank is the force required to cause current to flow in the circuit and is also referred to as electromotive force or difference of potential. Is it A, resistance, B, voltage, C, amperes, or D, ohms? Question 2. Blank is the property of a component, circuit, or material that opposes current flow. Is it A, resistance, B, voltage, C, amperes, or D, electromotive force? Question 3. Which of the following statements is correct? A. Resistance is measured in ohms. B. Voltage is measured in volts. C. Current is measured in amps. Or D. All of the above. Question 4. Current in a circuit increases when the voltage is increased, but decreases when the resistance is increased. Is that A, true, or B, false? Question 5. In a simple circuit with a 9-volt battery connected to a 3-ohm resistor, the current is blank amps. Is it A, 0.333, B, 3, C, 12, or D, 27? Section 2 of this course covers direct current, DC, and magnetism. A series circuit is formed when any number of resistors are connected end-to-end, so that there is only one path for current to flow. The resistors can be actual resistors or other devices that have resistance. The accompanying graphic shows 5 resistors connected end-to-end. There is one path of current flow from the negative terminal of the voltage source through all 5 resistors and returning to the positive terminal. Total resistance in a series circuit can be determined by adding all the resistor values. Although the unit for resistance is the ohm, different metric unit prefixes, such as kilo or mega, are often used. Therefore, it's important to convert all resistance values to the same units before adding. For the circuit in the accompanying graphic, the total resistance found by adding the resistance of all 5 resistors is 16,100 ohms. which is equal to 16.1 k-ohms. The current in a series circuit can be determined by using Ohm's law. First, total the resistance and then divide the source voltage by the total resistance. For the circuit shown in the accompanying graphic, the total resistance is 1000 ohms or 1 k-ohm. To find the current, divide 1000 ohms into 12 volts. The result is 12 thousandths of an amp or 12 milliamps. This current flows through each resistor in the circuit. The voltage measured across each resistor can be calculated using Ohm's law. The voltage across a resistor is often referred to as a voltage drop. The sum of the voltage drops across each resistor is equal to the source voltage. The accompanying illustration shows two voltmeters, one measuring total voltage and one measuring the voltage across R3. Note that you can calculate the voltage across R3 by multiplying the current, 12 milliamps, by the resistance, 250 ohms. The result is 3 volts. A parallel circuit is formed when two or more resistors are placed in a circuit side by side, so that the current can flow through more than one path. The accompanying graphic shows the simplest parallel circuit: a DC voltage source and two parallel resistors. There are two paths of current flow. One path is from the negative terminal of the battery through R1, returning to the positive terminal. The second path is from the negative terminal of the battery through R2, returning to the positive terminal of the battery. If the voltage and resistance of each resistor are known, the current through each resistor can be determined by dividing the voltage by the resistance of that resistor. In this circuit, the total current is the sum of the current flowing through R1 plus the current flowing through R2. The total resistance for a parallel circuit with any number of resistors can be calculated using the formula shown in the accompanying illustration. The total resistance divided into 1 is equal to the sum of all fractions formed by dividing each individual resistance into 1. To find the total resistance, divide the sum of these fractions into 1. In the unique example where all resistors have the same resistance, the total resistance is equal to the resistance of one resistor divided by the number of resistors. The accompanying illustration shows an example of a total resistance calculation for a circuit with 3 parallel resistors. In this example, R1 is equal to 5 ohms, R2 equal to 10 ohms, and R3 equal to 20 ohms. The total resistance calculation shown in red in the accompanying graphic shows that the total resistance for this circuit is approximately 2.86 ohms. It's useful to note that the total resistance for a parallel circuit is always less than the resistance of any single resistor. Current in each of the branches of a parallel circuit can be calculated by dividing the circuit voltage, which is the same for all branches, by the resistance of the branch. The total circuit current can be calculated by adding the current for all branches or by dividing the circuit voltage by the total resistance. The circuit shown in the accompanying graphic is the same as the one on the last page of this course, except that it now shows that the circuit voltage is 10 volts. The calculation shown in red in this graphic shows that the current through R1 is 2 amps, the current through R2 is 1 amp, and the current through R3 is 0.5 amps. Therefore, the total current is 3.5 amps. This is the same value you get when you divide the circuit voltage, 10 volts, by the total resistance, 2.86 ohms. Series parallel circuits are also known as compound circuits. At least 3 resistors are required to form a series parallel circuit. The accompanying illustration shows the 2 simplest series parallel circuits. The circuit on the left has 2 parallel resistors in series with another resistor. The circuit on the right has 2 series resistors in parallel with another resistor. Series parallel circuits are usually more complex than the circuit shown here, but by using the circuit formulas discussed earlier in the course, you can easily determine circuit characteristics. The accompanying graphic shows how total resistance can be determined for 2 series parallel circuits in 2 easy steps for each circuit. More complex circuits require more steps, but each step is relatively simple. In the example on the left, the two 10 ohm parallel resistors are replaced with an equivalent 5 ohm resistor. The simplified circuit has two 5 ohm resistors in series for a total resistance of 10 ohms. In the example on the right, the two 5 ohm series resistors are replaced with an equivalent 10 ohm resistor. The simplified circuit has two 10 ohm resistors in parallel for a total resistance of 5 ohms. Using the same two series parallel circuits as in the previous example, but with source voltages included, the accompanying graphic shows how Ohm's law can be used to calculate other circuit values. At this point, I'll pause on the screen for a minute to give you time to look through the calculations. Whenever a force of any kind causes motion, work is accomplished. If a force is exerted without causing motion, then no work is done. In an electrical circuit, voltage applied to a conductor causes electrons to flow. Voltage is the force and electron flow is the motion. The rate at which work is done is called power and is represented by the symbol P. Power is measured in watts, represented by the symbol W. In a direct current circuit, 1 watt is the rate at which work is done when 1 volt causes a current of 1 amp. As the accompanying graphic shows, from the basic formula, power equals current times voltage, two other power formulas can be derived using Ohm's law. Because E equals I times R, IR can be substituted for E in the P equals 1 times E formula, and the result is P equals I squared times R. Because I equals E divided by R, E divided by R can be substituted for I in the P equals I times E formula, and the result is P equals E squared divided by R. The accompanying illustration shows how power can be calculated using any of the three power formulas. In this example, with E equal to 12 volts, I equal to 2 amps, and R equal to 6 ohms, regardless of which of the three power formulas you use, the result is P equals 24 watts. The principles of magnetism are an integral part of electricity. In fact, magnetism can be used to produce electric current and vice versa. When we think of a permanent magnet, we often envision a horseshoe, a bar magnet, or a compass needle. But permanent magnets come in many shapes. However, all magnets have two characteristics. They attract iron, and if free to move, like a compass needle, a magnet will assume a north-south orientation. Every magnet has two poles, one north pole and a south pole. Invisible magnetic lines of flux leave the north pole and enter the south pole. Although the lines of flux are invisible, the effects of magnetic fields can be made visible. If a sheet of paper is placed over a magnet and our iron fillings loosely scattered on the paper, the fillings arrange themselves along the invisible lines of flux. The density of these lines of flux is greatest inside the magnet and where the lines of flux enter and leave the magnet. The greater the density of the lines of flux, the stronger the magnetic field. When two magnets are brought together, the magnetic fields around the magnets cause some form of interaction. As the accompanying graphic shows, when two unlike poles are brought together, the magnets attract each other. When two like poles are brought together, the magnets repel each other. An electromagnetic field is a magnetic field generated by current flow in a conductor. Every electric current generates a magnetic field, and a relationship exists between the direction of current flow and the direction of the magnetic field. The left-hand rule for conductors demonstrates this relationship. If a current-carrying conductor is grasped with the left hand, with the thumb pointing in the direction of electron flow, the fingers point in the direction of the magnetic lines of flux. A coil of wire carrying a current acts like a magnet. Individual loops of wire act as small magnets. The individual fields add together to form one magnet. The strength of the field can be increased by adding more turns to the coil, increasing the amount of current, or winding the coil around the material, such as iron, that conducts magnetic flux more easily than air. The left-hand rule for coils states that if the fingers of the left hand are wrapped around the coil in the direction of the electron flow, The thumb points to the north pole of the electromagnet. An electromagnet is usually wound around a core of soft iron or some other material that easily conducts magnetic lines of force. A large variety of electrical devices, such as motors, circuit breakers, contactors, relays, and motor starters, use electromagnetic principles. That concludes Section 2. Now for another knowledge check. Question 1. In a 120-volt DC circuit with 10 ohms of resistance, current is blank amps. Is it A, 1.2, B, 12, C, 120, or D, 1200? Question 2. In a circuit with a 10 ohm resistor in series with a 15 ohm resistor, total resistance is blank ohms. Is it A, 1.5, B, 6, C, 25, or D, 150? Question 3. In a circuit with 3 10 ohm resistors in parallel, total resistance is blank ohms. Is it A, 3.33, B, 20, C, 30, or D, 300? Question 4. In a DC circuit with a 20 volt supply and 4 ohms of resistance, the power is blank watts. Is it A, 5, B, 80, C, 100, or D, 320? Question 5. Unlike magnetic poles, blank each other. A, attract, or B, repel. This section of the Basics of Electricity course will cover alternating current and simple AC circuits with inductance and capacitance. The supply of current for electrical devices may come from a direct current DC source or an alternating current AC source. In a direct current circuit, electrons flow continuously in one direction. Voltage polarity for a direct current source remains constant. DC power sources include batteries and DC generators. By contrast, an AC generator makes electrons flow first in one direction, then in another. In fact, an AC generator reverses its terminal polarities many times per second, causing current to change direction with each reversal. Alternating voltage and current vary continuously. The graphic representation for AC is a sine wave. A sine wave can represent current or voltage, and there are two axes. The vertical axis represents the direction and magnitude of current or voltage. The horizontal axis represents time. When the waveform is above the time axis, current is flowing in one direction. This is referred to as the positive direction. When the waveform is below the time axis, current is flowing in the opposite direction. This is referred to as the negative direction. A sine wave moves through a complete rotation of 360 degrees, which is referred to as one cycle. Alternating current goes through many of these cycles each second. AC generators operate on the theory of electromagnetic induction. This simply means that when conductors are moved through a magnetic field, a voltage is induced into the conductors. Although commercial power generators are complex machines, for the purpose of explanation, a basic generator can be constructed of magnets, an armature, slip rings, brushes, and some type of resistive load. An armature is any number of conductors wound in loops which rotate through the magnetic field created by the magnets. For simplicity, one loop is shown in the accompanying illustration. If you track the rotation of the AC generator through a complete revolution of 360 degrees, you'd see that, during the first quarter of a revolution, voltage increases until it reaches a maximum positive value at 90 degrees. Voltage decreases during the second quarter of a revolution until it reaches zero at 180 degrees. During the third quarter of a revolution, voltage increases in the opposite direction until it reaches a maximum negative value at 270 degrees. During the last quarter of a revolution, voltage decreases until it reaches zero at 360 degrees. The number of cycles per second of voltage induced in the armature is the frequency of the generator. If the basic AC generator's armature rotates at a speed of 60 revolutions per second, the generated voltage will be 60 seconds per cycle. The recognized unit for frequency is hertz, abbreviated Hz. 1 hertz is equal to 1 cycle per second. Power companies generate and distribute electricity at very low frequencies. The standard power line frequency in the United States and many other countries is 60 Hz. 50 Hz is also a common power line frequency used throughout the world. The following illustration shows 15 cycles in a quarter second, which is equivalent to 60 Hz. The frequency is the same as the number of rotations per second if the magnetic field is produced by only two magnetic poles. An increase in the number of poles causes an increase in the number of cycles completed in a revolution. A two-pole generator completes one cycle per revolution, and a four-pole generator completes two cycles per revolution. In other words, an AC generator produces one cycle per revolution for each pair of poles. As previously discussed, voltage and current in an AC circuit rise and fall over time in a pattern referred to as a sine wave. In addition to frequency, which is the rate of variation, an AC sine wave also has amplitude, which is the range of variation. Amplitude can be specified in three ways: peak value, peak-to-peak value, and effective value. The peak value of a sine wave is the maximum value for each half of the sine wave. The peak-to-peak value is the range from the positive peak to the negative peak, and this is twice the peak value. The effective value of AC is defined in terms of an equivalent heating effect when compared to DC. Instruments designed to measure AC voltage and current usually display the effective value. The effective value of an AC voltage or current is approximately equal to 0.707 times the peak value. The effective value is also referred to as the RMS value. This name is derived from the root mean square mathematical process used to determine the effective value of a waveform. The instantaneous value is the value at any one point on the sine wave. The voltage waveform produced as the armature of a basic two-pole AC generator rotates through 360 degrees is called a sine wave, because the instantaneous voltage or current is related to the sine trigonometric function. As shown in the accompanying illustration, the instantaneous voltage E and current I at any point on the sine wave are equal to the peak value times the sine of the angle. The sine values shown in the illustration are obtained from trigonometric tables. Keep in mind that each point has an instantaneous value, but this illustration only shows the sine of the angle at 30-degree intervals. The circuits studied to this point have been resistive. Resistance and voltage are not the only circuit properties that affect current flow, however. Inductance is the property of an electric circuit that opposes any change in electric current. Unlike resistance, which opposes current flow at all times, inductance opposes changes in current flow. Current flow produces a magnetic field in a conductor. Any change in current causes a corresponding change in the magnetic field surrounding the conductor that induces a voltage in the conductor while the change is occurring. This self-induced voltage, sometimes called counter EMF, opposes the change in current. In a DC circuit, current may vary somewhat, but most significant current variations occur when the power is turned off or on. In an AC circuit, the current is constantly varying. All conductors have inductance. Therefore, as the accompanying graphic shows, electrical products such as control relays, transformers, and electric motors also have inductance. Many applications also use inductors, which are coils of wire wound for a specific inductance. For some applications, inductors are wound around a metal core to further concentrate the inductance. The inductance of a coil is determined by the number of turns in the coil diameter and length, and the core material. An inductor is usually indicated symbolically on an electrical drawing as a curled line. Inductance is designated by the letter L. The unit of measurement for inductance is the Henry, which is symbolized by the small letter H. In the accompanying circuit, an AC source supplies electrical power to four inductors. Total inductance of series inductors is equal to the sum of the inductances. Because 1 Henry is a relatively large amount of inductance, inductances are often expressed in millihenries or microhenries. The total inductance of inductors in parallel is calculated using a formula similar to the formula for resistance of parallel resistors. The accompanying illustration shows the calculation for a circuit with 3 parallel inductors. Capacitance is a measure of a circuit's ability to store an electrical charge. A device manufactured to have a specific amount of capacitance is called a capacitor. A capacitor is made up of a pair of conductive plates separated by a thin layer of insulating material. Another name for the insulating material is a dielectric material. When a voltage is applied to the plates, electrons are forced onto one plate. That plate has an excess of electrons while the other plate has a deficiency of electrons. The plate with an excess of electrons is negatively charged. The plate with a deficiency of electrons is positively charged. Direct current cannot flow through the dielectric material because it is an insulator. However, the electric field created when the capacitor is charged is felt through the dielectric. Capacitors are rated for the amount of charge they can hold. The capacitance of a capacitor depends on the area of the plates, the distance between the plates, and the type of dielectric material used. The unit of measurement for capacitance is the farad, F. However, because the farad is a large unit, capacitors are often rated in microfarads or picofarads. Connecting capacitors in series decreases total capacitance. The formula for series capacitors is similar to the formula for parallel resistors. In the accompanying circuit, an AC source supplies electrical power to 3 capacitors. Adding capacitors in parallel increases circuit capacitance. In the accompanying circuit, an AC source supplies electrical power to 3 capacitors. Total capacitance is determined by adding the values of the capacitors. Okay, we just finished up that section, so time for another knowledge check. Question 1. An AC sine wave voltage with a peak value of 294.2 volts has an effective value of blank volts. Is it A, 120, B, 208, C, 240, or D, 294.2? Question 2. A circuit with 3 mH, 4 mH, and 5 mH inductors in series has a total inductance of blank mH. Is it A, 0.78, B, 1.28, C, 12, or D, 60? A circuit with 3 mH, 4 mH, and 5 mH inductors in parallel has a total inductance of blank mH. Is it A, 0.78, B, 1.28, C, 12, or D, 60? Question 4. A circuit with 3 PF, 4 PF, and 5 PF capacitors in series has a total capacitance of blank PF. Is it A, 0.78, B, 1.28, C, 12, or D, 60? Question 5. A circuit with 3 PF, 4 PF, and 5 PF capacitors in parallel has a total capacitance of blank PF. Is it A, 0.78, B, 1.28, C, 12, or D, 60? This section of the basics of electricity will cover additional AC circuit concepts. In a purely resistive AC circuit, resistance is the only opposition to current flow. In an AC circuit with only inductance, capacitance, or both inductance and capacitance, but no resistance, opposition to current flow is called reactance, designated by the symbol X. Total opposition to current flow in an AC circuit that contains both reactance and resistance is called impedance, designated by the symbol Z. Just like resistance, reactance and impedance are expressed in ohms. Inductance affects current flow when the current is changing by producing a counter EMF, which is a voltage that opposes changes in current. In an AC circuit, current is changing constantly. Inductance in an AC circuit, therefore, causes a continual opposition to current flow, and that's called inductive reactance. As shown in the accompanying graphic, inductive reactance is equal to 2n times the frequency times the inductance. In a purely resistive circuit, current and voltage rise and fall at the same time. They are said to be in phase. For the circuit in the top illustration, there is no inductance. Therefore, resistance and impedance are the same. In a purely inductive circuit, voltage leads current by 90 degrees. Current and voltage are said to be out of phase. For the circuit in the middle illustration, impedance and inductive reactance are the same. All circuits have some resistance. However, in an AC circuit with both resistance and inductive reactance, voltage leads the current by more than 0 degrees and less than 90 degrees. For the circuit in the bottom illustration, resistance and inductive reactance are equal and voltage leads current by 45 degrees. Another way to say this is that current lags the voltage in a circuit with resistance and inductance. The exact amount of lag depends on the relative amounts of resistance and inductive reactance. The more resistive a circuit is, the closer it is to being in phase. The more reactive a circuit is, the more out of phase it is. Capacitors also oppose current flow in an AC circuit. This opposition is called capacitive reactance. As shown in the accompanying graphic, capacitive reactance is equal to 1 divided by 2n times the frequency times the capacitance. Therefore, the larger the capacitance or the higher the frequency, the smaller the capacitive reactance. For capacitive circuits, the phase relationship between current and voltage are opposite to the phase relationship for an inductive circuit. In a purely capacitive circuit, current leads voltage by 90 degrees. In an AC circuit with both resistance and capacitive reactance, current leads voltage by more than 0 degrees and less than 90 degrees. The exact amount of lead depends on the relative amounts of resistance and capacitive reactance. The more resistive a circuit is, the closer it is to being in phase. The more reactive a circuit is, the more out of phase it is. In the bottom illustration, resistance and capacitive reactance are equal and current leads voltage by 45 degrees. Impedance, Z, is the total opposition to current flow in an AC circuit. Impedance is often represented as a vector. A vector is a quantity that has magnitude and direction. An impedance vector diagram shows reactance and resistance vectors at right angles to each other, with the impedance vector plotted at some angle in between the reactance and resistance vectors. Resistance is plotted at 0 degrees, inductive reactance at 90 degrees, and capacitive reactance at negative 90 degrees. The accompanying graphic shows two circuits with equal values of resistance and reactance. The upper circuit has inductive reactance and resistance, and the lower circuit has capacitive reactance and resistance. The magnitude of the impedance vectors is determined by taking the square root of the sum of the squares of the reactance and resistance vectors. Although the magnitude of the impedance vector, 141.4 ohms, is the same for both circuits, the angles of the impedance vectors are different. For the upper circuit, the impedance vector has an angle of plus 45 degrees, but for the lower circuit, the angle is negative 45 degrees. Note the relationship between the impedance vector angle and the phase relationship between voltage and current for each circuit. Many circuits contain values of resistance, inductance, and capacitance in series. In an inductive AC circuit, current lags voltage by 90 degrees. In a capacitive AC circuit, current leads voltage by 90 degrees. When represented in vector form, inductive reactance and capacitive reactance are plotted 180 degrees apart. As a result, the net reactance is determined by taking the difference between the two reactances. The total impedance of the circuit can be calculated using the formula shown in the accompanying graphic. Once the total impedance is known, the current can be determined using Ohm's law. Keep in mind that because both inductive and capacitive reactance are dependent upon frequency, if the frequency of the source voltage changes, the net reactance changes. For example, if frequency increases, inductive reactance increases and capacitive reactance decreases. For the special case where the inductive reactance and capacitive reactance are equal, the circuit impedance is the total resistance. This type of circuit is called a series resonant circuit. Many circuits contain values of resistance, inductance, and capacitance in parallel. One method for determining the total impedance for a parallel circuit is to begin by calculating the total current. In a capacitive AC circuit, current leads voltage by 90 degrees. In an inductive AC circuit, current lags voltage by 90 degrees. When represented in vector form, capacitive current and inductive current are plotted 180 degrees apart. The net reactive current is determined by taking the difference between the reactive currents. The total current for the circuit can be calculated using the formula shown in the accompanying graphic. Once the total current is known, the total impedance can be calculated using Ohm's law. Keep in mind that because both inductive reactance and capacitive reactance are dependent upon frequency, if the frequency of the source voltage changes, the reactances and corresponding currents change. For example, if the frequency increases, the inductive reactance increases, and the current through the inductor decreases, but the capacitive reactance decreases, and the current through the capacitor increases. For the special case where the inductive reactance and capacitive reactance are equal, the inductive and capacitive currents cancel, and the net current is the resistive current. In this case, the inductor and capacitor form a parallel resonant circuit. In resistive circuits, power is dissipated in heat. This is called true power, or effective power, because it's the rate which energy is used. True power is equal to the current squared times the resistance. The unit for true power is the watt. Although reactive components do not consume energy, they do increase the amount of energy that must be generated to do the same amount of work. The rate at which this non-working energy must be generated is called reactive power. The unit for reactive power, the VAR, which stands for volt ampere reactive. The vector sum of true power and reactive power is called apparent power. Apparent power is also equal to the total current multiplied by the applied voltage. The unit for apparent power is the volt ampere, or VA. Power factor is the ratio of true power to apparent power in an AC circuit. This ratio is also the cosine of the phase angle. In a purely resistive circuit, current and voltage are in phase. This means that there is no angle of displacement between current and voltage. The cosine of a 0-degree angle is 1. Therefore, the power factor is 1. This means that all energy delivered by the source is consumed by the circuit and dissipated in the form of heat. In a purely reactive circuit, voltage and current are 90 degrees apart. The cosine of a 90-degree angle is 0. Therefore, the power factor is 0. This means that all the energy the circuit receives from the source is returned to the source. For the circuit in the accompanying illustration, the power factor is 0.8. This means the circuit uses 80% of the energy supplied by the source and returns 20% to the source. Another way of expressing true power is the apparent power times the power factor. This is also equal to I times E times the cosine of the phase angle. Transformers are electromagnetic devices that transfer electrical energy from one circuit to another by mutual induction. They're frequently used to step a voltage up to a higher level or down to a lower level. A single-phase transformer has two coils, a primary and a secondary coil. Energy is transferred from the primary to the secondary via mutual induction. The accompanying graphic shows an AC source connected to the primary coil. The magnetic field produced by the primary induces a voltage in the secondary coil, which supplies power to a load. Mutual inductance between two coils depends on their flux linkage. Maximum coupling occurs when all the lines of flux formed the primary coil cut through the secondary coil. To maximize the amount of coupling, both coils are often wound on the same iron core, which provides a good path for the lines of flux. The following discussions of step-up and step-down transformers apply to transformers with an iron core. There is a relationship between primary and secondary voltage, current, and impedance, and the ratio of transformer primary turns to secondary turns. When the primary has fewer turns than the secondary, voltage is stepped up from primary to secondary. For the circuit on the left, the transformer secondary has twice as many turns as the primary, and voltage is stepped up from 120 VAC to 240. Because the impedance of the load is also higher than the impedance of the primary, current is stepped down from 10 to 5 amps. When the primary has more turns than the secondary, voltage is stepped down from primary to secondary. For the circuit on the right, the primary coil has twice as many turns as the secondary coil, and voltage is stepped down from 240 to 120. Because the impedance of the load is lower than the impedance of the primary, the secondary current is stepped up from 5 to 10 amps. Transformers are rated for the amount of apparent power they can provide. Because values of apparent power are often large, the transformer rating is frequently given in kVA, kilovolt amperes. The kVA rating identifies the current and voltage a transformer can deliver to its load without overheating. The most common power supply stream used in residential applications in the U.S. today is a single-phase 3-wire supply system. In this system, the voltage between either hot, wire, and neutral is 120 volts, and the voltage between the two hot wires is 240 volts. The 120 volt supply is used for general purpose receptacles and lighting, and the 240 volt supply is used for heating, cooling, cooking, and other high demand loads. Up until now, we've been talking only about single-phase AC power. Single-phase power is used where power demands are relatively small, such as for a typical home. However, power companies generate and distribute three-phase power. Three-phase power is used in commercial and industrial applications where power requirements are higher than those of a typical residence. Three-phase power, as shown in the accompanying graphic, is a continuous series of 3 overlapping AC cycles. Each wave represents a phase and is offset by 120 electrical degrees from each of the other 2 phases. Transformers used for three-phase power require 3 interconnected coils in both the primary and the secondary. These transformers can be connected in either a Y or delta configuration. The type of transformer and the actual voltage depend on the requirements of the power company and the needs of the customer. The accompanying graphic shows the secondary of a Y-connected transformer and the secondary of a delta-connected transformer. These are only examples of possible distribution configurations. The specific voltages and configurations vary widely depending upon the application requirements. Well, that concludes the final section. Now we'll do a knowledge check and then jump right into the final exam. Question 1. Inductive reactance blank if either frequency or inductance is increased. Is it A, decreases, B, increases, or C, stays the same? Question 2. Voltage blank current in an inductive AC circuit. Is it A, leads, B, lags, or C, in phase with? Question 3. Capacitive reactance blank if either frequency or capacitance is increased. Is it A, decreases, B, increases, or C, stays the same? Question 4. Current blank voltage in a capacitive AC circuit. Is it A, leads, B, lags, or C, is in phase with? Question 5. The blank for a circuit is equal to true power divided by apparent power. Is it A, reactive power, B, real power, or C, power factor? Now it's time for the final exam. Question 1. Blank is a good insulator. A, copper, B, aluminum, C, silver, D, rubber. Question 2. A material with more protons than electrons blank. Is it A, has a negative charge, B, has a positive charge, C, has no charge, or D, may have a positive or negative charge? Question 3. In a simple electric circuit with a 12 volt supply and a 24 ohm resistor, current is blank amps. Is it A, 0.2, B, 0.5, C, 2, or D, 5? Question 4. The total resistance of a series circuit containing 3 10 ohm resistors is blank ohms. Is it A, 3.33, B, 10, C, 30, or D, 90? Question 5. The total resistance of a circuit with 3 30 ohm resistors in parallel is blank. Is it A, 3.33, B, 10, C, 30, D, 90? Question 6. The rate at which work is done is called blank. Is it A, energy, B, power, C, efficiency, or D, power factor? Question 7. Power in a simple 12-volt, 4-amp DC series circuit is blank. Is it A, 3 amps, B, 3 watts, C, 48 amps, or D, 48 watts? Question 8. Total opposition to current flow in an AC circuit with both resistance and reactance is called blank. A, resistance, B, reactance, C, impedance, or D, capacitance? Question 9. The total inductance of a series circuit containing 10, 20, and 40 mH inductor is blank. Is it A, 5.7 pF, B, 5.7 mH, C, 70 watt, or D, 70 mH? Question 10. Power factor is equal to blank. Is it A, true power divided by apparent power, B, apparent power divided by true power, C, true power times apparent power, or D, true power minus apparent power? Question 11. Which of the following external forces can cause electrons in the outer orbit of an atom to become free of their orbit? Is it A, movement through a magnetic field, B, friction, C, chemical action, or D, all of the above? Question 12. In a purely inductive circuit, blank. Is it A, current and voltage are in phase, B, current leads voltage by 90 degrees, C, voltage leads current by 90 degrees, or D, voltage leads current by 45 degrees? Question 13. In a purely capacitive circuit, blank. Is it A, current and voltage are in phase, B, current leads voltage by 90 degrees, C, voltage leads current by 90 degrees, or D, voltage leads current by 45 degrees? Question 14. A transformer with 120 volts on the primary and a 1:2 step-up ratio will have blank volts on the secondary. Is that A, 60, B, 120, C, 240, or D, 480? Question 15. 1 kiloamp is equal to blank amps. Is it A, 0.000001, B, 0.001, C, 100, or D, 1000? Question 16. 1 MV is equal to blank volts. Is it A, 0.000001, B, 0.001, C, 100, D, 1000? Question 17. Resistance is always expressed in blank. Is it A, farads, B, ohms, C, henries, or D, watts? Question 18. The peak value of a sine wave, blank. A, occurs once each cycle at all the positive maximum value. B, occurs once each cycle at the negative maximum value. C, occurs twice each cycle at the peak positive and negative maximum. Or D, is also known as the RMS value. Question 19. The unit of measurement for inductance is the blank. A, ohm, B, watt, C, farad, D, henry. Question 20. The unit of measurement for capacitance is the blank. A, ohm, B, watt, C, farad, D, henry. This is David Quatello at Siemens, and thank you again for taking the Siemens Quick Step Basics of Electricity course.